Hello and welcome. We are looking at dilations. Now, I've gone through this slide before for translations, reflections, and rotations. I'm actually not going to spend so much time talking about these three this time anymore, so you can look at those videos if you want to take a look at it. But I will point out something regarding this term isometry. So let's look at preimage, image, and isometry, these definitions. Preimage is a figure before transformation, so if these three were your original figures before some sort of transformation took place, such as this one's translation, moving these points down, reflections, going across some sort of axis of symmetry, such as this, and rotations, taking everything and moving them downward, like X goes there, and I said I wouldn't talk about it, now I'm talking about it. The idea, though, is that nothing is truly changing about the congruency of the corresponding parts. Angle A and angle A prime are both congruent. Segment CD and segment C prime D prime are congruent, etc. These are called isometries, when pre-image and image have congruent corresponding parts. Now, one of them, now all of these generate isometries. One of the transformations that does not is dilations, and that's what we're going to be looking at here. So if you take a look at these two if you take a look at those pentagons, isometries, triangles, isometries, trapezoid isometries, in this figure below with the two arrows, although corresponding angles are congruent, corresponding segments are not. So if we take a look at this top angle here and this top angle here, they're the same angle measure. Let's say they were 100 degrees or whatever, right? And these are even right angles here, congruent angles, but the segments now are different. Okay, so they don't generate isometries. We're going to talk a little bit more about what the segments do, though. They are not just random out of the ordinary things. They are proportional, and we're going to run into that a little bit. Let's say dilations produce similar objects. The preimage and image are similar. They are not congruent. Similar is an actual geometric term. Okay, let's start looking at dilation. It is a transformation whose pre-image and image are similar. Here we go. Its change in size can be calculated by a scale factor. I'm using the variable n every so often. I might, actually. I think some books use that. So scale factor. The scale factor ratio is calculated from image to pre-image. So meaning it's a fraction. You take the length of a part in an image, you divide it by the length of a corresponding part in its pre-image, and you will get the scale factor. Okay, so that means if we're looking at an image whose length is greater than the corresponding part of the pre-image, and you divide it, you would be getting a value greater than 1. And if that ratio is greater than 1, then it is an enlargement, meaning that your pre-image grew to become your image. If the ratio is less than 1, then it is a reduction. Don't worry, we will be doing plenty of examples of this. Okay, so let's go ahead and take a look at this example right here. What you're given are two triangles. If you can't really see the other triangle that's behind it, triangle ABC would ideally be in red. I wonder if there's a way I can bring it out here. No, I guess I couldn't. But triangle ABC would be in red. And triangle A prime, B prime, C prime down here is all in blue. So ABC, the pre-image, had a side length AB of 4 and a side length AC of 5. In fact, it still does. But after it's transformed and you take a look at the image, AB prime, segment addition postulate, is 4 plus 4. That's 8. So let's go ahead and start writing some things here. The entire length of this guy, and I'm sorry for that thing that pops up. I've tried to get rid of it. I've even tried to speed up my computer. It just doesn't happen. This whole side length of A prime, B prime is 8. A prime, C prime is 10. 5 plus 5. So if lengths like these are given, you can probably do a couple things with that. So let's take a look. 10. And AB was 4. And AC was 5. So what I'm going to do is calculate n for you guys. It is a ratio of image length to pre-image length. 8 over 4. This should be equivalent to the ratio here, and this is where we're going to start touching on the idea of similarity. 8 divided by 4 is the same as 10 divided by 5. That's 2. 2 is your scale factor. That means that every length in this thing grew twice as large as it did before, which also means it's an enlargement. So the scale factor of the dilation is 2. It is an enlargement. And, by the way, if they said that this length here was 6, the length of this entire B prime C prime, they might want to know what this is here. Well, here's where similar comes into play. You can also think about proportional sides. Because triangles are similar, they grew, these angles, if you think about this as, I'm saying too many things at once. If these were right angles, then these are parallel lines right there. And if that's true, then these are corresponding congruent angles right there. I'm just talking out of making sure that you understand that these things all correspond with one another. So these have congruent angles, and A and A prime are obviously the same angle as well. So all angles are congruent in similar polygons, but the sides are proportional, which means whatever the length is from 8 to 4, that's the same as 10 to 5, right? That's 2. 2 over 1. That's your ratio. So whatever the image length is, like this one's 6, the pre-image would then be half as much. If you need to do some algebra, you could cross multiply and divide by 2. You're going to get 3, right? X is 3 because double its length is 6. So that's just answering some questions for you in that big example there. That's one example of dilation. Now, we're going to be talking about the center of dilation just in a moment here. I'm going to go to the next slide, but I'll have you know, because I might not go back to this one, that A prime, A was the center of dilation right here. You'll see why as I move on. Okay, here's another example, and before I do this one, I want to start talking about the center of dilation. Here we go. Every dilation has a center. Every one. This exists where the pre-image and image have corresponding vertices. Now, it might not be on a vertex. In this past case, it was. It was on where A and A prime were the same thing. But the point is, if there is any sort of point after the enlargement or reduction where one point didn't move, that point is its center. So if you think about this one more time, as this grew outward, A stayed at the same place where A prime is. Now here in this example, the center of dilation will be the place that did not move after the enlargement or reduction. All other corresponding vertices travel the same direction away from the center, where the vertices in the image are n times the distance away from the center, compared to that of the vertices in the pre-image. What does that mean? Well, let's also figure this out. On a graph, calculate the slope and distances away from the pre-image points to the center to determine the image. Whew. All right, here we go. That's more of the last example here, but we are going to be using these points and figuring all them out. So if we're talking about corresponding vertices, you can tell these two correspond. This point's at 0, 2, this point's at 0, 1. Over here, you have this point at 6, 0, this point, corresponding point, at 3, 0. This point here is at 3, negative 2. This point here is at 6, negative 4. And finally, this point here is at negative 2, negative 2. This point is at negative 1, negative 1. So the question becomes, what is the center of dilation, and what was the growth, what was the scale factor? So the way I'm going to find out the center of dilation here, what I was talking about was they travel the same distance away from the center. Now the blue quadrilateral is a dilation image of the red quadrilateral, which means we started on red and we went inward toward blue to make this happen. So if they go the same direction, I'm going to start focusing on red here. I'm going to start mapping onto blue. I'll just start drawing straight all the way through. Because what's going to happen here is you're going to find one point that is the same for all of them where they are all meeting. That point is its center. That's where they were all growing out from. The center, however, did not grow, did not change at all as we did dilation. Actually, we did reduction. So as it shrank, as it reduced. So you can kind of see as I'm starting to map all these points here, you could use a straight edge to do this. Where are they all meeting at? The answer is the origin. The origin is the center of dilation. Okay. Now that's important not just to state, but it's also important to know because when you're trying to find out what the scale factor is, we have to pick some set of points, corresponding points to determine how much it reduced. Because remember, red was the pre-image. So I could go with distance formula on you guys and figure these out. Or you could kind of just take a look and venture a guess and recognize what it is. If I take a look at these two corresponding points, this was at 6, 0, so that distance away from the center is 6. Well, this distance away from the center is 3. So far, I'm taking a guess that the scale factor The n from image to preimage, 3 over 6, is 1/2. Let's double check that and make sure that that always works. What's 1/2 of 0, 2? Well, that's 0, 1. Now notice I'm going to take half of 0 and half of 2. What's half of 6, negative 4? Half of 6 is 3. Half of negative 4 is negative 2. Looks like this pans out. So the scale factor is 1/2. You multiply any of these by 1/2, then you've reduced this thing to half of what it was. Now, I just want to make sure you understand it's not half of the area, just half of the lengths. Okay, just half of the lengths. In fact, let's look back at this triangle one last time. What if I drew a few more right triangles in here? Remember, the scale factor was 2. I doubled every length. But did I double the area? What is the area of this triangle right here? It's 1/2 base times height, right? 1/2 3 times 4, so that's 6. The area of this triangle is 6 square units. What's the area of the blue triangle? 1/2 base times height. That's 1/2 6 times 8. 6 times 8 is 48. So the area of this one is 48 square units. Now, as I doubled my lengths, looks like I multiplied my, oh, whoops, I have to take half of that, I'm sorry. 48 over 2 is 24. Anyway, now as I've doubled my length, I have to multiply 6 by 4 to get my ratio of my two areas. So the areas aren't the same as the lengths, and that's going to be hit on another topic at some other point, not right now. But just realize that it would take 4 of these right triangles, if I kind of just jimmy them in. Here's one triangle, here's a second one, and if I draw a third one right here, I ideally created 2 more. I didn't do this perfectly. But if you notice here, it takes 4 of these, 1, 2, 3, 4, 4 of these triangles to make the biggest triangle. That's why the ratio of areas is different. So don't say that just because something is twice as big in area, or if you say something's twice as big, you have to specify. Are you talking about length? Are you talking about area? Perimeter, area, or volume? You have to determine. We're talking about perimeter. Okay, final example here. Calculate the slope and distances away from the pre-image points to the center to determine the image. All right, in this one here, we are going to draw the image after the dilation. The scale factor will be 3. The only difference is this time the center is not going to be at the origin. So it's not just as simple as saying, oh, just triple your points. Because our center is not at the origin. Our center is now off the origin. It's right there. What we're going to have to do is find out what the distances of these are relative to this to what my new center is. I might as well treat this as my new origin. If you've watched my rotation video, then you know exactly what I'm talking about here. If I made kind of new axes right here, ignore the old black XY axes. I don't want to look at them anymore. I want to look at these 2 axes right here and treat this as my new quote-unquote origin. Because what I want to do is find the distances away from this center point with regard to P, G, and Z. So what I'm going to do here is figure out, okay, if this point was, now this isn't really 3, 0, right? This point is 1, 1. But if this point was coined as 3, 0, what I want to do is triple this distance away from here because the scale factor is 3, and I'll say P prime is at 3 times 3, 0 times 3, which is 9, 0. So this is going to be 1, 2, 3. I'm sorry, that's 2 units away. I didn't even do that right. 2, 0, triple that, that's 6. I'm sorry. 6, 0. So 1, 2, 3, 4, 5, 6. So P prime is way out here. Now, is that point really 6, 0? No, that point is 1, 2, 3, 4, 5, 1. P prime is really at 5, 1, but the hidden agenda is to, treat this like it's at 2, 0 and 6, 0 so you can actually plot its point, right? I can get rid of these lines later. In fact, I will as soon as I'm done with all this. But I want you to recognize that I'm doing everything relative to this new center. G is like it's at 1, negative 2. So if I triple my points away from there, in fact, this might not even fit on here. I have to go down a little bit. If I triple my points away from there, G prime will be 1 times 3 away from that center, negative 2 times 3 away from that center, which is at 3, comma, negative 6. Now it's not at the real 3, negative 6, it's at the pseudo one that I've made. 1, 2, 3, 1, 2, 3, 4, 5, 6. So way down here. So it looks like I couldn't fit it on my original scale there. Z is 1 over to the left, 1/2 up. So this point is at negative 1, comma 1/2 relative to my center, not the origin. So Z prime will be at negative 1 times 3, comma 1/2 times 3, which is negative 3, comma 3/2. So from here I'll go 3 over to the left, 3.5 up, which is right there, and there's Z prime. To confirm you kind of did it right, think about what I talked about before regarding slope needs to be the same. Calculate the slope in distances away from the pre-image to the image. So this should follow along the same path, just as this should follow along the same path, and this should follow along the same path. As long as they do and you got your distances, I think you're good to go. So let's go ahead and start connecting the other points to draw the full triangle. This is your last example. And Z, Z prime to P prime, like so, and Z prime to G prime, and G prime to P prime. And as you can see, this was a growth not from the center. No, if this was a growth from the center, 3 away would have been right here. 3 away, I'm just showing you, would have been right here, and 3 away would have been about right there. So it's not from the original origin. No, if I remove all this other stuff, you might not be able to locate its center as quickly anymore. But its center was at some place different. And that was this point right here, negative 1, 1. And that's where it grew from. So again, what I had to do was calculate relative distances away from there to make it happen. Fiend.